Perception tells a robot what may be happening. Planning decides what to do about it. That gap is enormous. A robot has to choose actions that reach a goal while respecting geometry, time, energy, rules, moving people, and uncertainty. Good planning is not merely finding a route. It is choosing a safe, feasible future in a world that will not stand still. Task planning works at the level of goals. Pick the blue bin, open the door, deliver the tray. Motion planning works at the level of continuous movement. Where should the arm, wheels, or legs travel without collision? Separating these layers keeps decisions manageable, yet they must communicate. A task may be logically correct, but physically impossible from the robot's current pose. A star search explores a graph using both distance traveled and an estimate of distance remaining. On a grid map, it can efficiently find a route around walls and blocked aisles. Its strength is clarity and completeness in a known discrete space. Its weakness is that real robots have turning limits, continuous dynamics, and moving obstacles that do not fit neatly into simple squares. Rapidly exploring random trees, RRT, grow branches through difficult configuration spaces and can quickly discover a feasible route. RRT star improves routes toward lower cost. Probabilistic roadmaps, PRM, precompute useful connections for repeated queries. These algorithms shine for robot arms and complex spaces, where enumerating every possible pose would be impossible. Feasibility comes before elegance. Hybrid a star adds vehicle-like motion primitives, so a car does not plan impossible sideways moves. Trajectory optimization starts with a candidate trajectory and adjusts it to minimize collision risk, jerk, time, or energy while satisfying dynamics. Modern systems commonly use a search method to find a workable corridor, then optimization to refine a smooth, executable motion. Task planners break a request into actions with preconditions and effects. Serve a drink may become locate cup, navigate to counter, grasp cup, avoid spill, deliver, and verify handoff. Each action is grounded against current perception and capabilities. If the cup is absent or the path is blocked, the plan must branch, ask for help, or try a recovery rather than blindly following a script. Robots score choices across competing factors. The fastest path may consume too much energy. The shortest arm motion may pass too close to a person. A high-reward maneuver may carry unacceptable risk. Safety constraints set hard boundaries, objectives rank the options that remain. Making those trade-offs explicit gives teams a way to inspect and improve behavior instead of calling it intuition. Uncertainty changes the plan. If a corridor might contain a person behind a blind corner, the robot should reduce speed or collect another observation. If its grip estimate is uncertain, it should choose a more stable grasp. Belief space planning reasons over possible states rather than one assumed truth. It is more computationally demanding, but physical systems need that caution near real consequences. Modern physical AI rarely bets on one planner. Classical algorithms provide constraints and verifiable structure. Neural networks supply perception priors, cost functions, and fast proposals. LLMs translate natural language and broad knowledge into task hypotheses. World models roll out likely outcomes. A safety layer checks the final proposal. The stack is powerful because each component covers a different weakness. A plan is a proposal, not a promise. New sensor data can reveal a moving cart, a slipped object, or a blocked doorway. Receding horizon planning repeatedly optimizes a short future, executes a small portion, observes again, and replans. This loop keeps a robot responsive without requiring an impossibly perfect forecast of the entire future from the start. Consider a warehouse robot asked to fetch a tote. It chooses the task sequence, finds a route, predicts forklift traffic, slows near blind corners, reserves enough battery for return, and reroutes when a pallet blocks an aisle. The visible behavior looks simple. Underneath, perception, search, optimization, uncertainty estimation, and safety rules are negotiating every second. Constraints encode what a robot must never violate: collision boundaries, joint limits, traffic rules, stability margins, no-go zones, and force limits. They differ from soft preferences such as shorter travel time. Treating safety as an explicit constraint keeps optimization from trading away a critical boundary merely because another option looks slightly faster or cheaper. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Planning turns a robot's understanding of the world into purposeful action. Task planning decides the sequence. Motion planning finds feasible movement. Search, sampling, and optimization generate candidates. Risk, energy, time, and safety select among them, and because reality changes, the system replans. That is how a machine becomes deliberate rather than merely reactive. The cost function expresses trade-offs among distance, smoothness, energy, clearance, delay, and task success. Poorly designed costs create surprising behavior, such as a vehicle that takes an uncomfortable route to save seconds. Teams inspect candidate trajectories, tune terms against real examples, and keep hard constraints separate from rewards whenever a violation is unacceptable. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Planning near people requires more than avoiding collision. A helpful robot maintains personal space, signals its intent through legible motion, avoids sudden reversals, and anticipates that people may change direction. Human-aware planning uses conservative forecasts and comfort-aware costs. The result is behavior that feels predictable and cooperative, which is essential for trust in shared spaces. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Before execution, a separate validator can check the plan against current maps, dynamic limits, policy rules, and safety envelopes. Runtime monitoring continues that check as the action unfolds. This independence is important when neural proposals or language-generated tasks are involved. A compelling suggestion is not permission to move hardware without a grounded feasibility test. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. The key engineering habit is to inspect not only the selected plan, but also the rejected alternatives, their costs, and their safety margins. That evidence makes behavior explainable. It lets operators understand why a robot slowed, waited, rerouted, or requested help, and it provides a disciplined basis for improving future decisions.